It begins with silence. Not the kind of silence you hear when the world goes quiet at night. No, this is deeper. A silence so complete it stretches across billions of light years. And in that silence, something stirs. A star dies. Not quietly, not peacefully. It screams into the void, a supernova explosion so bright it outshines entire galaxies. And from that firestorm of light and fury, something is born. Something so dense, so strange, so powerful that even the laws of physics struggle to describe it. This is the neutron star. Not a black hole, not a white dwarf, but something in between. A cosmic phantom forged in the heart of stellar death, smaller than a city, heavier than a star, spinning faster than your kitchen blender, and magnetic beyond imagination. This is the story of the universe's most extreme object, a place where matter behaves in ways we can barely comprehend, and where the line between science and science fiction vanishes. Let's go back to the beginning. Every neutron star starts as a giant, a massive star, at least 8 times heavier than our Sun, burning through its fuel at a terrifying rate. These stars live fast, burn bright, and die young. Some last only a few million years. Our Sun, it will shine for 10 billion. But these giants don't have that luxury. Deep in their cores, hydrogen fuses into helium, then carbon, oxygen, neon, all the way up to iron. And here, everything stops. Iron doesn't release energy when fused. In fact, it absorbs it. So, when the core becomes mostly iron, the star's internal furnace shuts off. No more outward pressure, no more balance. And in less than a second, gravity wins. The core collapses, inward, faster than anything you've ever seen. The outer layers of the star crash down at nearly 1/4 the speed of light. Then, boom, the rebound, the shockwave, the supernova. For a few dazzling weeks, this dying star becomes brighter than everything else in its galaxy combined. And when the light finally fades, something remains. A tiny, invisible dot. Denser than anything in the known universe. This is the birth of a neutron star. Now, let's talk about size, because this is where things get weird. Imagine taking the entire mass of our Sun, 330,000 times the mass of Earth, and crushing it into a ball just 20 kilometers across. That's about the size of a city. New York, London, Tokyo. All that mass squeezed into something you could drive around in an hour. That's a neutron star. But how? How can matter be that dense? Well, under normal conditions, atoms are mostly empty space. The nucleus is tiny. The electrons orbit far away. But when a star collapses, gravity becomes so strong that it overpowers even the forces that keep atoms apart. Electrons are forced into protons, they merge, and they form neutrons, hence the name neutron star. The entire star becomes a sea of neutrons, packed together like marbles in a jar, but with no space between them. This isn't just solid matter, it's neutron matter. A substance so exotic, we've never recreated it on Earth, not even in the most powerful particle colliders. And what's inside? We don't know for sure. Some scientists think the core might be made of quark-gluon plasma, a primordial soup of particles that existed just after the Big Bang. Others believe it could contain strange matter, a hypothetical form of matter that could be more stable than anything in our universe. If that's true, then neutron stars might not just be dead stars. They might be the most stable objects in existence. But here's the thing, we can't see inside. Not directly. We can only infer from gravity, spin, and radiation. So the core of a neutron star remains one of the greatest mysteries in astrophysics. Now, let's talk about gravity. On Earth, gravity pulls you down at about 9.8 meters per second squared. Jump and you come back down. Drop a ball and it hits the floor. Simple. But on a neutron star, gravity is 200 billion times stronger. If you could stand on its surface, which you can't, by the way, you'd weigh hundreds of billions of tons. You'd be crushed into a smear of atoms in a fraction of a second. Even light struggles to escape. The surface is so curved by gravity that you could theoretically see the back of the star. Light bends all the way around it. And time? It slows down. Thanks to Einstein's theory of general relativity, time moves slower in strong gravitational fields. So if you could hover near a neutron star, somehow surviving, your watch would tick slower than someone far away. You'd age slower, just like in Interstellar. But unlike a black hole, you could escape if you had enough speed. There's no event horizon, no point of no return. Just an object so extreme, it bends reality, but doesn't break it. Now, let's talk about rotation. When a massive star collapses, its spin speeds up, just like a figure skater pulling in their arms. The core, once rotating slowly, now spins hundreds of times per second. The fastest neutron star ever recorded, Pulsar J748-2446 it spins 716 times per second. That means a full rotation in just 1.4 milliseconds. Faster than your heart beats, faster than a bullet leaves a gun. And the surface is moving at nearly a quarter the speed of light. At that speed, the centrifugal force should tear it apart. But gravity is so strong, it holds everything together. Barely. These spinning neutron stars are called pulsars, and they're nature's most precise clocks. Here's how they work. Neutron stars have powerful magnetic fields, not aligned with their rotation axis. As they spin, beams of radiation shoot out from their magnetic poles, like cosmic lighthouses. If those beams sweep across Earth, we detect a pulse of radio waves, X-rays, or gamma rays. Regular, precise, sometimes accurate to within a billionth of a second. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. She thought it might be a signal from aliens. They even nicknamed it LGM-1, Little Green Men. But it wasn't aliens. It was something even more incredible. Since then, we've found over 3,000 pulsars, most in our galaxy, some in binary systems, others drifting alone through interstellar space. And they're not just scientific curiosities. Pulsars are so stable, astronomers use them to test Einstein's theories, detect gravitational waves, and even navigate spacecraft. In 1977, NASA launched the Voyager probes with golden records, but they also included a map using 14 pulsars as cosmic landmarks, so any intelligent life that finds them can trace back to Earth. Talk about leaving a calling card. Now, let's talk about magnetism. Earth's magnetic field is about 1.5 Gauss, a fridge magnet, around 100 Gauss, an MRI machine, up to 30,000 Gauss, a neutron star, typically a trillion Gauss. That's 1,000,000 times stronger than anything we can make on Earth. But some neutron stars are even more extreme. They're called magnetars. These are the most magnetic objects in the universe, with fields reaching a quadrillion Gauss. That's 1,000. To understand what that means, imagine standing 1,000 kilometers away from a magnetar. Your body wouldn't just be pulled. The magnetic field would distort the very atoms in your body. Electrons would be ripped from their orbits. Chemistry would break down. You'd cease to exist as a living being. Not because you were torn apart, but because your molecules couldn't hold together. And if a magnetar erupted, which they do, the effects could be felt across the galaxy. On December 27, 2004, a magnetar called SGR 1D06-20 erupted. It was 50,000 light-years away, on the other side of the Milky Way. Yet, the burst of gamma rays hit Earth so hard, it briefly disturbed our ionosphere. It was the brightest extrasolar event ever recorded in human history. For a tenth of a second, it released more energy than the Sun does in 50,000 years. And yet, the star survived. Magnetars are unstable. They crack under their own magnetic stress. Their crusts, made of iron nuclei and electrons, shift and fracture like tectonic plates on Earth. But instead of earthquakes, they produce starquakes. These quakes release massive bursts of energy, gamma rays, X-rays, detectable across thousands of light-years. And here's the wild part. We think magnetars might be the source of fast radio bursts, mysterious millisecond flashes of radio waves from deep space. Some of them repeat, others don't. We still don't know exactly what causes them. But many scientists believe magnetars are the prime suspect. In 2020, astronomers detected a fast radio burst coming from within our own galaxy, and it lined up perfectly with a known magnetar. The evidence is piling up. So while pulsars are lighthouses, magnetars are cosmic grenades, ticking, unstable, and ready to explode. Now, let's talk about what happens when neutron stars aren't alone, because sometimes they have company. In binary systems, two stars orbit each other. When one explodes and becomes a neutron star, the other may survive and continue orbiting. Over time, the neutron star can begin pulling material from its companion. Gas spirals in, forming a disk around the neutron star, an accretion disk. As it falls, it heats up to millions of degrees, glowing in X-rays. These systems are called X-ray binaries, and they're some of the brightest X-ray sources in the sky. But here's where it gets wild. As matter falls onto the neutron star, it can trigger a thermonuclear explosion on the surface. A Type I X-ray burst. It's like a hydrogen bomb, but powered by an entire star. The bursts can last seconds to minutes, releasing more energy than the sun does in a day. And if enough material accumulates, the neutron star might spin even faster. We call this recycling. Old, slow pulsars can be spun up to millisecond speeds, becoming millisecond pulsars. Some spin hundreds of times per second, yet are billions of years old. But there's an even more dramatic fate. When two neutron stars orbit each other, they slowly spiral inward, losing energy to gravitational waves. After millions of years, they collide. And when they do, it's one of the most violent events in the universe. In 2017, LIGO and Virgo, the gravitational wave detectors, picked up a signal from two neutron stars merging 130 million light-years away. It lasted just a minute, but in that minute they confirmed Einstein's predictions, detected gravitational waves, and saw a flash of light across the spectrum, from gamma rays to radio waves. This was the first time we observed a kilonova, a new type of explosion. And what did it create? Gold, platinum, uranium, elements heavier than iron. We used to think supernovae made these, but now we know neutron star mergers are the universe's primary gold factories. Every ounce of gold in your jewelry, it likely came from two neutron stars that collided long before Earth formed. And what's left after the merger? It depends. If the combined mass is under about 2.5 solar masses, it might form a bigger neutron star, possibly a hypermassive neutron star that spins wildly before collapsing. If it's heavier, it collapses into a black hole. But for a brief moment, milliseconds, it might form something even more exotic, a quark star or a blitzar, theoretical objects we haven't confirmed yet. The merger also sends out gravitational waves, ripples in space-time itself. By studying these, we're learning how matter behaves at extreme densities. It's like doing a physics experiment with an entire star. Now let's talk about the strange stuff, the things we're still trying to understand, because neutron stars aren't just extreme. They're laboratories of the impossible. Take superfluidity. Inside a neutron star, neutrons may flow without friction, like a liquid that never stops moving. Scientists believe the core could be filled with a superfluid, a state of matter that exists near absolute zero, but here at millions of degrees. How? Because at such high densities, quantum effects dominate. Neutrons pair up and move as a single quantum entity. No viscosity, no resistance. And because the star is rotating, this superfluid can form quantum vortices, tiny whirlpools that only exist in the quantum world. Even stranger, the outer core might contain superconducting protons, electric current flowing forever without resistance. This could explain the star's powerful, long-lasting magnetic field. And then there's the crust. It's not rock. It's a lattice of iron nuclei, crushed so hard they form exotic shapes. Nuclear pasta. Yes, nuclear pasta. As you go deeper, the nuclei get squeezed into sheets, like lasagna, then tubes, like spaghetti, then bubbles, like anti-spaghetti. Scientists call it gnocchi, waffles, and Swiss cheese phases. It's the densest pasta in the universe, and it's under such stress that it can crack, causing starquakes and glitches in the pulsar's spin. Sometimes a pulsar suddenly speeds up, a glitch. We think this happens when the superfluid inside transfers angular momentum to the crust, like a spinning ice skater pulling in their arms. But the details? Still a mystery. And what about the atmosphere? Some neutron stars have a thin layer of plasma, just centimeters thick, but hot enough to emit X-rays. We've used telescopes like NASA's NICA to map the surface of pulsars, measuring their size and mass with incredible precision. One pulsar, J0032451, was found to be about 26 kilometers wide and 1.3 times the mass of the Sun. Another, J0742 plus 6620, is the heaviest known, 2.35 solar masses. That's pushing the limit of how heavy a neutron star can be before collapsing into a black hole. These measurements are helping us solve the equation of state of neutron star matter, the relationship between pressure, density, and temperature. It's one of the holy grails of astrophysics, because it tells us what matter becomes when it's squeezed beyond anything possible on Earth. Now, let's zoom out. Neutron stars aren't just oddities. They're essential to the universe. They're the endpoint of stellar evolution for medium-heavy stars. They recycle matter into space through supernovae and kilonovae. They forge heavy elements. They test the limits of physics. And they may even help us find new physics. For example, some theories suggest that dark matter could accumulate in neutron stars and cause them to collapse into black holes. Others propose that neutron stars could contain axions, hypothetical particles that might explain dark matter. And if strange matter exists, a form of matter made of up, down, and strange quarks, then neutron stars might actually be strange stars, and if one were to touch normal matter, it could convert it into strange matter, a chain reaction, a strangelet, disaster, Don't worry, this is extremely unlikely. But it shows how neutron stars sit at the edge of known physics, where theory meets the unknown. So where are they? We think there are over 100 million neutron stars in our galaxy alone. But most are dark, cold, dead. Only the young, active ones, pulsars and magnetars, glow brightly enough to detect. They're scattered across the Milky Way, some near star-forming regions, others flung into space by supernova explosions. A few are even hypervelocity, kicked out at millions of kilometers per hour. And some might be closer than we think. The nearest known neutron star, RxJ 1856.5 3754, about 400 light-years away. It's not a pulsar, it's a radio-quiet neutron star, visible only in X-rays and ultraviolet. A dark, lonely wanderer. We've also found neutron stars in globular clusters, dense balls of old stars. And in the center of supernova remnants like the Crab Nebula, home to the famous Crab Pulsar, spinning 30 times per second, powering the entire nebula with its energy. Every time we look deeper, we find more. And with new telescopes, like the Square Kilometre Array, the James Webb Space Telescope, and future gravitational wave observatories, we'll uncover even more secrets. So what have we learned? Neutron stars are not just dead stars, they are cosmic extremes. They are laboratories of density, gravity, and magnetism. They are timekeepers, gold makers, and lighthouses in the dark. They challenge our understanding of matter. They test Einstein's theories. They connect us to the violent history of the universe. And they remind us, the universe doesn't play by Earth rules. It's stranger, denser, more violent, and more beautiful than we ever imagined. So the next time you look up at the night sky, don't just see stars. See the ghosts of giants. See the crushed hearts of suns. See the pulsing lighthouses of the cosmos, because somewhere out there a neutron star is spinning, flashing, burning, waiting. And in its silent rhythmic pulse, the universe is telling us its deepest secrets. If you've made it this far, thank you. You've just journeyed to one of the most extreme places in existence. But the story isn't over. Every year, new discoveries rewrite what we know about neutron stars. New telescopes, new detections, new mysteries. So stay curious. Look up, and never stop wondering what lies beyond the stars. If you enjoyed this journey, share it with someone who loves space. Subscribe for more deep dives into the cosmos. And remember, in the universe full of wonders, neutron stars are among the strangest and the most magnificent. Until next time, keep exploring.